Let's quickly do 3 more examples. This one is mixed, not pure antiderivative, not autonomous. The right-hand side, f of ty, literally depends on both t and y. Now, for example, f of 1, you got to take both the t and y coordinates into account. You get 1 plus 1 is 2. At the point 1, 2, that's on the same vertical line, you get something different. 1 plus 2 is 3. At the point 2, 1, that's on the same horizontal line as the original point, you get something different. 2 plus 1 is 3, etc. Can you solve the differential equation? Here's the syntax for trying to get Mathematica to solve it. Remember, you got to use double equal signs when solving equations in Mathematica. Using a single equal sign will mess things up. Don't do it. If you accidentally do it, you're going to have to clear the memory, clear the kernel. Evaluation, quit kernel to clear the memory because you've messed things up. Use double equal signs when solving equations. You do need these square bracket t's both here and actually here as well in Mathematica, in spite of the fact that we did not put of t there. Mathematica needs to explicitly be instructed to know that y does depend on t. By hand, we don't write it here, in part because it's traditional not to. In part, it's also a good pedagogical reason not to. Pedagogy meaning teaching and learning. Because if we put y of t there, that would confuse us as far as making the slope field. If that were y of t, that would be confusing. Mathematica says that's a general solution. Y equals -1 minus t plus c e to the t. If I was going to write that by hand, I'd probably put the c e to the t first. I'd write y equals, c e to the t minus t minus 1. Can that be solved? Can that be found by separating variables? It turns out no. Separation of variables doesn't work here, even though it's a fairly simple looking expression. You try to separate variables, because of the plus sign, it messes things up. It won't work. If it were t times y, then you could separate variables. But being t plus y messes things up. There are other techniques, in fact, 2 other techniques that I can think of to solve it that you'll learn if you take diffeq or diffeq with linear algebra. One that comes to mind prominently is something called the method of integrating factors, but that's for a different class. If you get Mathematica to draw the slope field, here's what it looks like. Taking notes by hand, you can just quickly do a rough sketch here, and the solutions look about like this. Oh, I didn't draw that one very well. Here's better. Ignore that. You should practice drawing these as well as you can. It doesn't mean you're going to get it perfect. You're just hoping for pretty good. There's no equilibrium solution here, but there is a special solution that looks like a linear function like this, but its slope is not 0. Hey, that's the function when c is 0, -t minus 1. Slope of -1, intercept of -1 as well. There. By the way, the c here does not equal the initial condition. If y of 0 equals 1, for example, c ends up equaling 2. So the c is not the same as the initial condition for this example, but you can use the initial condition to solve for c. Question? This doesn't have a a horizontal asymptote, but it's got a slant asymptote as t goes to minus infinity. It approaches the slanted line. So sometimes solutions do have slant asymptotes. Two more examples quick. T squared minus y. Can Mathematica solve it? T squared minus y. Yep. There's a general solution. I use DSolve instead of DSolve value this time. It's not a big deal. Here's what the slope field looks like. A little trickier looking. Got to be careful. Solutions are going to look, say, like this in here. And actually, I believe if you draw enough solutions in here, it becomes fairly clear that this doesn't have a slant asymptote, doesn't have a horizontal asymptote or a slant asymptote, but it does have a curved asymptote. Have you ever seen a function with a bunch of functions with a curved asymptote? These functions all are approaching something somewhere in here that's a curve. Last example. This one's a slope field, actually. T minus y squared. What happens with Mathematica? Something unexpected. Although, maybe by now we should expect something weird. Bessel functions. Ugh. What's going on there? The solution is not an elementary function. That's what's going on. So how do we graph it? We'd have to use either technology to graph this crazy function or draw a slope field. Here's what the slope field looks like. Oh, isn't that pretty in here? Very pretty. Some solutions going about like this, going up there. Other solutions going down here. I guess there's got to be some curved solution that's sort of being spit out in here, something about like that maybe. Kind of pretty. The moral of the story is you can use the technology to graph solutions even when you can't find their formulas. We'll get some practice on Monday. See you then.